One of the most powerful yet counterintuitive ideas in all of physics is wave-particle duality. It states that whenever a quantum propagates through space freely, without being observed and measured, it exhibits wave-like behavior, doing things like diffracting and interfering not only with other quanta but with itself. However, whenever that very same quantum is observed and measured, or compelled to interact with another quantum in a fashion that reveals its quantum state, it loses its wave-like characteristics and instead behaves like a particle. First discovered in the early 20th century in experiments involving light, it's now known to apply to all quanta, including electrons and even composite particles such as atomic nuclei. But the story of how we discovered wave-particle duality doesn't begin and end in the early 20th century, but rather goes back hundreds of years, to the time of Isaac Newton. It all began with an argument over the nature of light, one that went unresolved, despite both sides declaring victory at various times, until we came to understand the bizarre quantum nature of reality. While wave-particle duality owes its origin to the quantum nature of the universe, the human story of how we revealed it was full of important steps and missteps, driven at all times by the only source of information that matters: experiments and direct observations. Here's how we finally arrived at our modern picture of reality. In the 17th century, Isaac Newton championed the particle theory of light, suggesting that light is composed of tiny particles called corpuscles. Yet around the same time, Dutch scientist Christiaan Huygens proposed that light behaves as a wave. This debate persisted for centuries, with experiments and observations gradually tipping the scales. Fast forward to the 19th century. Thomas Young's double-slit experiment in 1801 demonstrated that light could create an interference pattern, a hallmark of wave behavior. Picture a wave propagating through water, such as in the ocean it appears to move linearly, at a particular speed and with a particular height, only to change and crash against the shore as the water's depth lessens. Back in 1678, Dutch scientist Christiaan Huygens recognized that these waves could be treated, rather than as linear coherent entities, as a sum of an infinite number of spherical waves, where each spherical wave became superimposed atop one another along the propagating wavefront. Huygens noted the existence of phenomena like interference, refraction, and reflection, and saw that they applied equally well to water waves as they did to light. And so he theorized that light is a wave as well. This provided the first successful explanation of both linear and spherical wave propagation, both for water waves as well as for light waves. However, Huygens' work had limitations. It could not explain why the waves only propagated forwards, not backwards. He could not explain edge effects or why and how diffraction occurred, and his idea of light could not explain the existence of polarization, which is easily observed as sunlight reflects off bodies of water. The idea that light is a wave was born with Huygens and became quite popular across the European continent upon his treatise's publication in 1690. Yet, it didn't catch on elsewhere due to the presence of a much more famous competitor. Isaac Newton, with his corpuscular theory of light, dominated the scientific discourse of the time. In 1704, Isaac Newton published his groundbreaking treatise on optics, based on experiments he first presented in 1672. Rather than a wave, Newton described light as a series of rays or corpuscles that behaved in a particle-like fashion. Newton's deductions in optics were direct inferences from meticulously performed experiments focusing on phenomena such as refraction and diffraction. By passing light through a prism, Newton was the first to demonstrate that light was not inherently white and merely altered by its interactions with matter to produce color. Instead, he showed that white light itself was composed of all the different colors of the spectrum. In one of his most famous experiments, Newton passed white light through a prism, revealing a vivid spectrum of colors. He then recombined these colors to form white light again, proving that white light is a mixture of all colors. He performed further experiments on refraction with prisms and lenses, diffraction with closely spaced sheets of glass, and color mixtures using both lights of individual colors and pigment powders. Throughout the 1700s, Newton's ideas became popular worldwide, heavily influencing figures such as Voltaire, Benjamin Franklin, and Lavoisier. But at the end of the century, from 1799 to 1801, scientist Thomas Young began experimenting with light, making two enormous advances in our understanding of light in the process. The first, arguably most famous advance, is illustrated above. Young performed what's known as the double-slit experiment with light for the first time. By passing light of a monochrome color through two closely spaced slits, Young was able to observe a phenomenon that's only explicable through wave behavior, the constructive and destructive interference of that light in the pattern it produces in a fashion that depends on the color of the light being used. Young was further able to prove, through quantitative investigation, that what we perceive as the color of light is in fact determined by the wavelength of that light. That wavelength and color, barring the mixture of different colors, were directly related to one another. While Newton's conception of light still had its advantages, it was clear that the wave theory of light had its advantages too, and succeeded where Newton's corpuscular theory did not. The mystery would only deepen as the 19th century unfolded. In the early 19th century, the debate over the nature of light was far from settled. The French Academy of Sciences held a pivotal essay competition in 1818 to uncover the true nature of light. Physicist Augustin-Jean Fresnel decided to enter, presenting a detailed essay on the wave theory of light. Fresnel's work incorporated Huygens' wave principle and Young's principle of interference, offering groundbreaking insights into the behavior of light. However, one of the judges, Simeon Poisson, a staunch supporter of Newton's corpuscular theory, sought to discredit Fresnel's ideas. Poisson argued that Fresnel's theory led to an absurd prediction. If monochromatic light was passed through a diverging lens, widened and directed around a spherical obstacle, a bright luminous point would appear at the center of the shadow. This point, known today as Poisson's spot, seemed so ludicrous that Poisson believed it invalidated the wave theory entirely. Despite Poisson's skepticism, the French Academy of Sciences decided to test this prediction. To everyone's astonishment, the experiment confirmed Fresnel's theory. A bright spot did indeed appear at the center of the shadow, validating the wave nature of light. This unexpected outcome not only vindicated Fresnel, but also marked a significant turning point in the scientific community's understanding of light. Poisson's spot, once considered an absurd calculation, became a crucial piece of evidence supporting the wave theory. After the unexpected revelation of Poisson's spot, the scientific community was still abuzz. However, there were 5 men on the committee, and one of them was François Arago, an abolitionist, politician, and a man who would, in 1848, become president of France. Arago was moved by Poisson's argument against Fresnel's idea, but not in the reductio ad absurdum sense that Poisson intended. Instead, Arago became motivated to actually perform the experiment himself. He set out to create a monochromatic light source, widen it in a spherical fashion, and pass it around a smooth, small sphere to see what the results of the experiment were. To the great surprise of perhaps all, Arago's experiment revealed that the spot does in fact exist. Moreover, it appeared of identical brightness to the unobstructed light, varied in size only as a function of the light's wavelength, distance to the screen, and size of the sphere. Additionally, it contained concentric, faint rings that resulted from further interference arising from the various wave fronts. Huygens' ideas had finally been placed on a solid theoretical footing, and had been developed into a full-fledged theory that could now account for phenomena such as polarization. As the 19th century progressed, the scientific community experienced a surge of groundbreaking discoveries, particularly in the fields of electricity and magnetism. The contributions of luminaries such as Ampere, Faraday, Gauss, Coulomb, and Franklin laid a robust foundation for what would become one of the century's most monumental scientific achievements: the formulation of Maxwell's equations and the birth of electromagnetism. When these particles move, they create electric currents, which in turn produce magnetic fields. Furthermore, changing magnetic fields can induce electric currents, and changing electric fields give rise to what Maxwell termed the displacement current, a magnetic field that responds in a unique manner. In the 1870s, these principles culminated in a revolutionary insight: under specific conditions, electromagnetic radiation could emerge. This radiation consisted of oscillating in-phase electric and magnetic fields that propagated at a universal speed, the speed of light in a vacuum. Maxwell's equations illuminated a new understanding. Light was not merely a wave, it was an electromagnetic wave traveling at a constant speed. Of course, physics didn't end with the discovery of classical electromagnetism, and the dawn of the 1900s would bring with it the earliest stages of the quantum revolution. One of the key aspects of this new conception of our reality came from none other than Albert Einstein himself, whose 1905 treatise on the photoelectric effect would forever change our understanding of light. Taking a conducting metal plate, Einstein was able to show that shining light on it caused electrons to spontaneously be emitted from the metal, as though these electrons were being kicked off by the light that struck them. Clearly, with enough energy, the electrons were becoming unbound from the metal they were a part of. What Einstein did next was nothing short of brilliant. When he varied the intensity of the light, he noted that this changed the number of electrons kicked off, but not whether they were kicked off. When he varied the wavelength of the light, he noted that beyond a certain wavelength, no electrons would get kicked off, irrespective of how high the intensity got. And when he varied the wavelength of light in the opposite direction to short wavelengths, he noted that electrons were always kicked off, irrespective of how faint and dim the intensity got. It was as though light was made up of individual energy packets, known today as photons, which carry energy in proportion to their frequency, or inversely proportional to their wavelength. Even though light propagated as a wave, it interacted with matter like a corpuscle, or particle, bringing about the beginnings of the modern idea of wave-particle duality. In the quest to understand the dual nature of reality, the modern double-slit experiment stands as one of the most profound demonstrations. It turns out that photons, electrons, and all other particles exhibit this peculiar quantum behavior known as wave-particle duality. If you observe and measure them during their journey, or force them to interact and exchange energy and momentum with other quanta, they behave as particles. But if you don't, they behave as waves. This duality is perhaps best exemplified by the modern version of Young's double-slit experiment. Unlike the original experiment that relied on monochromatic light, the modern version can even be performed with single particles, such as photons or electrons, passed through a double slit one at a time. In this setup, if you perform the experiment without measuring your particles until they reach the screen, you will find that they reproduce the classic interference pattern once you've accumulated enough individual quanta. Bright spots, which correspond to the locations where large numbers of particles land, are spaced apart by dark bands where few to no particles land, consistent with the notion of an interference pattern. However, if you measure whether the quantum passes through slit 1 inch or slit 2 inches during its journey, the result is profoundly different. The interference pattern disappears, replaced by 2 distinct lumps, one corresponding to particles that passed through the first slit and the other to particles that passed through the second slit. When you don't measure a quantum, but rather simply allow it to propagate, it behaves like a wave. A classical wave that interferes with not just other waves, but also itself, exhibiting wave-like behavior such as diffraction and superposition. However, when you do measure a quantum, or otherwise compel it to interact with another quantum of high enough energy, your original quantum behaves like a particle, with a deterministic particle-like trajectory that it follows, just as tracks in particle physics detectors reveal. So, is light a wave or a particle? The answer is yes. It's both. It's wave-like when it's freely propagating, and it's particle-like when it's interacting, a set of phenomena that's been probed in an enormous variety of ways over the past 100 years or so. Despite the proposal of hidden variables to attempt to reconcile wave-particle duality into a single deterministic framework, all experiments point to nature still being non-deterministic, as you cannot predict the outcome of an unmeasured wave-like trial with any more accuracy than the Schrödinger's equation's probabilistic approach. Wave-particle duality began in the 1600s, and despite our attempts to pin down the true nature of reality, the answer that the universe itself reveals is that our quantum reality is both simultaneously and really does depend on whether or not we measure or interact with it.